Hey everybody, happy February. Turn on your microphones and say hello.
Hello,
Hello.
Ken. Hello,
Hello.
crew.
I can.
Hi, Chip.
Hey guys,
Hi,
can
Chip.
you hear me okay?
Yes.
Yeah.
Okay.
Super. Just use that as a chance to adjust your audio and make sure everything works. Okay, what do we got? It's February. So today I had a couple of topics, so I made an agenda, brief agenda, which looks like this. So we'll talk a little bit about the new Flip module, which Ari was probably chasing around just a minute ago in manufacturing. Ray Allen has a topic, brief one. Chip's going to talk about his work on an Allen Bradley compatible Propeller 2 board. And I will share a project we've been working on with Paul Flickema of Northern Arizona University, if he's here today.
Man,
Oh, great. Hi, Paul.
hey,
So these are in no particular order. So before we continue, what other items do people want to talk about that are worthy of an agenda, or can we just handle them loosely after these topics? Okay, crickets. Ray Allen, you're here? Yep, he's
Yep.
here.
Just
Okay,
joined.
good. So we're all here. And then Chip also has another topic. He's making a bug fix on the compiler. So Chip, do you want to talk briefly about the bug fix, and then I can go back and pick up, get my
Yeah,
stuff
sure.
together? Okay.
Sure. Let's see here. Let me pull it up.
Sorry to catch you off guard with no advance
Oh,
warning.
that's fine. That's fine. Um, okay, let me use the screen share here. Okay, here I put up a new V52. This bug had been discovered quite a while back, but I've been busy working on this PLC stuff, so I haven't been able to fix it. But basically, I wasn't popping the stack right under these kinds of circumstances. So two things happened. I went in, it took me like a couple nights to really look at that code well and understand exactly what was going on. And then because it's like performing a surgery. I don't want to go in there casually and start messing with stuff. So I understood exactly what the trouble was, got it all lined out, made the changes to the compiler. And so now all of these next with integer values and quits work as planned. But I also changed the way they work a little bit. Uh, it used to be that next one would mean the current loop, but I didn't want to do that because it wasn't very sensible to me. So now when you specify an integer after next or quit, it means how many outer levels to go to. So if you say next one, that means do a next in the first outer loop. If you say next four, it would do the next in the fourth outer loop. If you just say next, it confines the behavior to the repeat loop that you're in. Anyway, so this is posted on OBEX now, and it seems I'm getting the same results. Maca had figured out what the trouble was, and a while back, I think it was, well, I don't remember what month, it was a couple months ago. Anyway, the compiler's updated now. This little bug is fixed. The behavior has changed a little bit, I think, for the better. I ran it by Maka. He said that'd be fine with him. He didn't know that anyone was using this feature yet anyway. So uh, it's now what I think is most sensible, where nothing means current loop, one means the first outer loop, two means second outer loop, and so on.
Hey, Chip, just for clarity, you put that on OBEX, not in the forums. Is that right?
Yeah, that's right. I'm doing it like we're supposed to now. So
Good
wait,
boy.
where did I have this stuff here? Um, Oh, wait, I thought I had a list of, here we go. Yeah. Right here is the OBEX link. So this is the spin 2 documentation. So right here is the link. So it's there. So if we go there now, let's see. What do I do? Open. There we go. Yeah, here it is. So this is on the OBEX. Okay, so I'll quit sharing this. Any questions? It's kind of a simple thing.
Chip, would anybody expect any backward code compatibility issues or anything?
I don't think so, because the feature was broken in some cases. And you know, this is not a common thing that a programmer would use, but in certain circumstances, it can really save the day because it allows you to structure your code in such a way where you don't have to fall out of loops and then check flags. You can just, you know, go right out to where you want to be.
Cool. Any questions for Chip? Well, thanks, Skippy.
You're welcome.
Okay, brief topic here. Everything takes longer than you think it will. Back in November, I thought we would have these ready in December. This is the Flip Revision C. And so it's a USB-C update to the Flip module. And they're in production now. We had a bit of a snafu, had to tune one component. So a start and stop in production. But we got that part, and now they're being built. Ari's going back to take a look, I guess, or he's just going for a walk, or he's going to get his lunch, or he's going to harass that nice person. I don't know where he's going. Okay, looks like maybe Terrell's working on them. Anyway, USB-C, and we can provide 1.5 amps of current when it's available through the USB-C connector. And we widen the VIN range, 5 to 16 volts, has lower standby current and unique ID support for those who want IDs in their products. And those are the biggies. So we're still trying to clear out a few of the old Rev Bs. We have 57 in stock, but depending on what our customers want to do, maybe we'll just retire these at some point and mystery box them and then go on to revision C. Ari, how far out are these from being done? You'll have to unmute yourself if you want to tell us anything.
There. So yeah, they are in production, and we have finished units. We just fixed an issue with a testing procedure and reworking some units. But yeah, we are good to go.
Cool. Okay. Any day.
Ken, the ID feature, is that going to be accessible in the Blockly IDE?
I don't think so, unless it's something you can get with Serial IO. That's a good question. I don't know. I don't know if Michael's here either, but
Did you get that going with using the new kind of EEPROM?
we did. We changed the FTDI chip. And I could look at the spec for it.
Oh, so it's in the FTDI chip?
I believe so. I'll find out when we're talking about other things and then come back to this.
Okay, because I just also noticed that new EEPROMs have a 128-bit ID you can get with them. I don't know if I haven't, so I just wonder if that's maybe what you're using.
So maybe before we put them into production, we just run a little routine and pull all the IDs and label each one.
If you'd like.
I would like. I want to track that inventory.
Oh, is this an ID that you get from the computer talking to the board, or the chip, the P1 has access to?
I think the latter, that the P1 has access to. I don't know if you could generate the ID or not.
Okay,
So
that must be in the EEPROM then. I
you
think
guys
it's
have overextended my understanding of this, but I'll find out and come back. So okay, next topic. Let's talk about the TreeGuard project. So I'm just going to share a picture of a board and then introduce Paul. Okay, so you can see the TreeGuard now. First, I'd like to introduce Paul Flickema from Northern Arizona University. Hi, Paul.
Well, I'm actually a consultant to the university. I don't work for them anymore.
Nice. And I think your history I read a while ago is you specialize in embedded systems and measurement.
Well, that's kind of new for me, actually. I used to work in communications and signal processing, so hardware and software is a little new for me.
Well, you did well with this. So this project, generally what it is, it's part of a state-funded effort in Arizona to monitor a destructive grub in their trees. And we'll let you kind of expand on it, Paul. Just talk briefly about what's on the board and what we did to make it with you. Then they can ask you all the questions. But you've been already doing something like this, so we took this with you to the next pre-production level using as many off-the-shelf parts as we could to keep the price down. And some of the things are on it that you could see. There's a prop plug connection in the upper right. There's a ADC on it. And we added an ADC, right? We did not use the P2.
Right. So Michael Middleton integrated what was on the ADC chip from AKM that you guys already had as a board that would plug into the breakout board. And so that's at the bottom of this board, and you can see the screw terminals where we can bring signals into the ADC. It's an ADC that goes up to 192 kilosamples per second, which we really wanted for this project because we wanted to be able to get sounds up to 35, 40 kilohertz.
And then it also has a DAC for real-time listening,
Yes,
which
yes.
is our regular add-on board,
Yeah, and that's optional.
and a real-time clock.
And that
Right.
has also been moved in from a plug-in board that Parallax designed. So Michael is able to integrate that hardware onto this board.
That's down in the lower left corner.
Right.
And it has we went back and forth about how we communicate with these, but basically these sit in boxes up in trees and the user has to come up to them and get data and then go away and maybe change the battery. So we spoke about Bluetooth for a while, but we wound up using our Wi-Fi module. So that's the socket in the upper left.
Yes.
And we have a button for reset to wake it up and then give the user time to connect. And I think we may have put an RGB LED with that. I'm not sure. Maybe.
Right. There's a RGB button that interfaces and the plug on the lower right, the white plug. And so, and Michael very helpfully has provided code to interface with that RGB button. I have not integrated it yet. I just got the boards yesterday.
You're going to be busy. And
Yeah.
then we together we found a box and enclosure for this, and we built 10 of these. So we started the project in September, and then we finished it last week. We made one pre-production, pre-prototype, and then tested it, got it working. Then we made 10 more, and then we packed them up and shipped them to you. And I think the concept here was that we would do these as protos, but kind of progressed prototypes using as much off the shelf as we could to save design costs, and then allow you to go develop more firmware. And then you'll come back, presumably, and then we can turn it into more surface mount and lower the cost. So
Yes, if we get to production levels, larger volumes, but I have to say right now, again, I haven't started testing it yet, but I'm super happy with the final result and the process. And I'll just say a little bit of background. When we started this project, we were trying to come up with a way to do the proof of concept, and we were able to prove the concept with a Raspberry Pi and a plug-in board. But it turned out to, number one, use way too much power, and number two, the driver was closed source, and we weren't able to optimize the analog to digital conversion. And so I did a lot of searching on different possibilities for a board and a microcontroller, and it's kind of true that I just stumbled on Parallax and found out that there was an ADC board that would do what we needed and an open source driver. And that was huge. And I really like working with Parallax because when there's hardware, there's usually a driver that goes with it, like, for example, the real-time clock. And so this has been very helpful in building our prototype system.
thanks, Paul. Yeah, and Paul, you mentioned too, so Michael did the design, which was really handy because we were able to save a lot of time and money because he's done 70 such PCB designs for Parallax, including many of the modules, like the P2 Edge that plugs into this board. So this saved us some time on the hardware side, and it should save time for you, of course, on the software side with the drivers, but we definitely saved a lot in the hardware, which is great, and got this going faster because if it had been all surface mount, it probably would have taken us a few months longer to finish it and been quite a bit more expensive.
Yeah, I'm very happy with the setup that we have with the P2 Edge module. And I think it's a 6-layer board. And so we're able to basically have 2 levels of complexity because the host board is what I call it now, where the P2 Edge plugs into. I believe Michael's able to do it with only 2 layers. So that saves money. And so, yeah, it's been a really good process. And um, a lot of care has been taken in working with me to get to this point.
Thanks. Well, we make chip available for driver help when you get stuck, as planned in the beginning.
Great. And Michael has already provided some demo code, uh, test code and demo code for the Wi-Fi, for the RTC. I already have RTC on my existing code, so I'll be able to adapt that. And also there's some code supplied by Michael, maybe from Chip, I don't know, to do the RGB button. So I'm looking forward in the next while to integrate this into my application.
By RGB button, you mean the WS2812 kind of part?
Well, I
Huh.
don't know what the part number is, but it's about an 18 millimeter button. You can see it
Oh,
right
I see.
It's
Okay,
right here.
so it has
Yeah.
an addressable LED in it, an RGB LED.
Yeah.
Yes.
Okay. Yeah, we
And
can.
as I mentioned, Michael has sent some test code, which I haven't integrated or tested yet, but it basically exercises the 3 colors and allows you to basically capture an edge or a level using the button. So
Yeah, I saw a lot of
looking forward to
pins on
that.
that. I saw a lot of pins on that connector, so it might just be individual LEDs.
It could be, yeah.
Hmm.
Yeah. I think you're right, Ray. And it's an
I think
expensive
it's
little
6
button too.
pins, yeah.
So you imagining solar power or LiPo or how are you going to power this thing?
So We don't know yet. We do have the potential to put some smaller batteries in the lid of the box, but we also have the possibility of having an external supply. We even talked about for really long-term monitoring a motorcycle battery on the ground. So I'm pretty happy with the flexibility that we're looking at.
Hey, Paul, could you also speak to the difficulty of measuring or counting, noticing these little grubs in the trees?
Yeah, so that's been the focus of my work, and we're still, I would say, in early days. So the larvae and sometimes the adults of these wood-boring insects make noises when they chew. When they chew the tissue of the tree, and it's often just below the bark. And my colleague at NAU is a forest entomologist and has worked for quite some time with using piezo transducers to capture those sounds. And if the bug is far away from the piezo, then the sounds can be very weak. So a lot of my work has been focused on, okay, how do we detect these so that we can determine if a tree is infected or not?
Question,
Just
Paul.
a little
So I
background.
live in,
This is a huge
Paul,
issue where, um, for example, some of the borers are just wiping out entire species of trees right now. One is the emerald ash borer, which is killing all the ash trees in the US and also attacks olive trees in California. So this is why the Forest Service in Arizona is interested.
what other critters? I live in northern Arizona, Paul, near Prescott. What other than the emerald ash borer, what other ones are out here?
So what Rich tells me is that every tree has its pest, but another big one is the pine bark beetle, which has been going on for a long time. And it's attacked large forests. When you're out in Arizona or Utah or Colorado, you can sometimes see whole stands that are just completely dead due to the pine bark beetle. So there are so many trees with so many species of bugs.
Cool, thank you.
And when do these bugs become noticeable? Is it the spring?
Um, Depending on temperature, they'll work through the winter. Um, I've been out with Rich and we've listened to them in January, deep inside the trees sometimes. There is a life cycle to these bugs, which is pretty complex because you have the adults flying. That's how they spread. They bore into the tree, lay their eggs, and then the larvae start about the size of less than a piece of rice and end up the size of your finger. Um, and then I guess you could say convert or transform to adults and fly out of the tree and spread to other trees.
I'm looking at the pupa of one of those guys. That's pretty big.
Yes.
Wow, the larva. Oh, oh God, this is an ugly bug.
And of
Thank you.
course, you'd like to catch them before they get big, right? Um, and yeah, so a big focus in the future is going to be improving the analog side of the process where we have the piezo that's attached to the tree. And that's where I'm working with a mechanical engineer who has done a lot of work with piezoelectric energy harvesting. Sensing is different than energy harvesting, but we're making some progress there.
So, Paul, question. If they find a tree that's been infested, what do they do they take the tree out or what?
Well, there are different strategies. There are chemicals that you can introduce into the ground around the tree. Uh, quite expensive. You have to pump the chemicals into the ground. Um, Sometimes they actually try to cut the trees that are infected to save the rest of the stand. Another application of this is in city parks, where if you have a tree that's been there for 50, 80 years, a tree that's really valuable, you might catch it, we hope, and cut off the limb that's infected and save the rest of the tree.
And drought makes it all way worse, right?
Yes, drought and temperature. We've had a crazy warm winter here in Arizona. Um, and so, and also a complete lack of snow so far. So the trees are going to be really stressed due to those factors this coming year, it looks like.
Any questions for Paul? Okay, well, Paul, thanks so much. We remain here to help you out as you get going with the code, of course. And
Appreciate that. I have an email I need to send to Michael about the Wi-Fi. That'll be sending just a question there, but um, you guys have been great. Thank you.
yeah, you're very welcome. So if others watching this have products that they want to create, we can help you here. As I mentioned about 6 months ago, we have some capacity on our pick and place line. And some of that's just because Terrell keeps getting better and better and faster, and he takes really good care of our equipment. Um, and that's enabled us to do more. So if you're making a product or in that business and you need to create a specification for what you want to do, and we can help you figure out what hardware is best to do that with, and all the parameters and constraints we go over, and then we put that in a spec, and then we try to stick to that specification and get it done. Because it's really important to have hardware, as you all know, in your hands you could start working with. Then you can change it. But sometimes there's nothing to do, or you just can't get started. You can't show it to anybody. You can't get more funding. You can't build interest around what you're doing. It's nice to get hardware started. And that's what we're able to do here. So it was nice that we were able to make a spec and then stick with it pretty closely too. So thanks again, Paul. Ray, do you want to talk about spin 2 on a P1 and then we can move to chip?
Okay. Yep. We try to. Do I need to enable video to share? I don't think so.
Oh yeah, I need to stop sharing. So here you go.
Oh. I guess that works.
Oh yeah.
Looks good.
Okay. Yeah. So I started. I got this device that I decided was better with a P1. I've been in P2 world mainly for a long time now, but I'm P2 world, and then I'm jumping back into P1 world, and well, I decided I like spin 2 a whole lot better than spin 1. So this is an adventure to see if I can use spin 2 with the P1, and this has been there a while, but I just started doing the deep dive into it. I'm just getting started, but it seems like it's working and has potential. So I thought I'd share what I found so far. Let's see, how do I advance the slide? Oh, okay. So right now there's only one compiler that this works with, and it's Flex Spin. So thanks to Aerosmith for doing it. I guess this has probably been there for a long time, forever, but I just started playing with it. And so I think, to me, like, the one thing is to have, especially for particular devices, like things you might plug into the P2 header, or things you might like quick things, or just in general, it'd be nice to have one spin 2 code that'd be good for P1 and P2. And you know the things, the main thing, the Spin2 has a lot of advantages, but I just kind of the main ones for me is like requiring parentheses on methods. This makes code a lot easier to understand, especially when it's complex. You're looking at a name, you don't know what it is. This helps a lot.
Yeah, that was a problem. I kind of saw that myself later.
Then another thing is more easily control turning off and on pins instead of having to deal with NA and out A. There's inherent support for floating point. Then the C style greater than equal. Then the operators, some of these other operators have easy to remember names instead of trying to have to look up these symbols. And this is kind of a surprise. The debug works. So that's
Debug
actually,
works.
yeah, so that's nice.
Whoa.
And some inline assembly.
Does the debug work with multiple cogs running?
Well, okay. Well, I just got started with this. I assume so, but I don't know. I don't want to say.
That's amazing. You got all that working. That's a lot of work.
So the current limitations is basically it's only supported by FlexProp. Although I did figure out how to get it to work with SpinTools IDE, which is a lot nicer in terms of visuals. So like here's a really biggie for me is like you can this like you know this thing with out A and in A, it works, but it's kind of this is where people, the first thing we want to do when you get a board is like turn on an LED, and when you have to deal with the in A and out, it gets a little complicated, but this makes things a whole lot easier. And I figured out you don't want that underscore in front of wait MS. So the print debug works. So that's nice. And also the X dot thing is the Spin2 way of addressing any bit in any variable. So that works also. So that's nice. Inline assembly works. That was probably already there in P1, but it still works in Spin2. So that's nice. This is how you configure SpinTools to use it. And I used tool number 1, which you invoke with Alt-1 to compile, and then tool number 2, which you invoke with the keyboard stroke Alt-2 to invoke that, and that loads it. And then here's an example showing the debug. And it says down here cog 0, so I assume, I don't really know if it works. I haven't tried it in another cog, but it looks like it potentially could work. The Spin2 soft floating point works, so that's kind of nice. I tested that out here. Yep. So there's always going to be things that aren't going to work on P1 that are going to have to be different between P1 and P2, and that's where the precompiler can help separate this stuff, especially things like clock setting and assembly. These are obviously going to be different, and this is a way to combine them into one code. Okay, and yeah, and the graphical debug works. Wow, this is kind of surprising. This only works in the SpinTools IDE. So the sine wave stuff was a bit of a challenge, but I just took I made my own version of QSign for P1 that takes the sine generator thing out of the P1 manual and puts it into inline assembly. And I was able to get all these things to work.
Wow.
It's a little bit slower on P1, but it works. The one thing that there isn't is an input, like the P2 debug has an input, but FlexProp doesn't have keyboard input or mouse input at all. And Eric says that's a difficult thing, so I'm not going to hold my breath for that. But at least the output works. So anyways, things just getting started with this. It's looking good. One thing you might think is, well, the Spin1 library for P1 is so extensive. Maybe it's a mistake to ignore that. But you can the advantage here is you can include P1 spin objects as sub-objects in your main spin2 file. And I think you can also include C and base objects, but I haven't tried that yet. So that was kind of it. Just wanted to say this kind of looks good. I don't really expect anybody else to do it, but for me, I like it. So I might see if how far I can push this. And that's kind of it.
That's pretty neat. Boy, I didn't know that was possible. It's amazing what kind of things people can do these days. I mean, it's hard for me to know my own code. I can't figure out how they learn someone else's stuff and then make it work again in some other way.
Ray, thank you. How far is this project going to go?
Well, I'm trying to slowly building up. Well, okay, so I'm slowly building up some quick drivers because I'm also a big fan of this quick stuff. So I know Parallax hasn't really done it yet, but let's see if my video doesn't work, does it? But anyway, so I made a board with a P1 board with USB-C. That's why I'm glad to see your flip with USB-C because I definitely think that's like the future there, and and that makes everything look new. So it's good to have USB-C. But my boards and Johnny Mac's doing this too. We put in quick connectors, and that's Parallax hasn't done that, but it's an easy way to add in all kinds of peripherals, like 100 different things. And so I'm putting that in there, and I'm trying to make a library of spin2 drivers that can drive these things, these quick things, for instance, in spin2 for both P1 and P2. And also, some of the this board I made, it also has the P2 style headers on it. And I think Johnny Mac is doing that too. And some of the Parallax peripherals actually work on P1 as well, like the control board, the LED matrix. So these, there's probably more, but those things at least I've already tested and they work on P1. So that's kind of what I'm playing with right now.
That's pretty good.
All right. Just looping back to the question about the ID number on the flip revision C. I haven't looked at the documentation yet, but I just put in the two parts that make this possible, the FTDI chip and the EEPROM. I pasted into the chat. So I'm sure one of you can answer that now. But looking back at the original spec, it says about the EEPROM, update the EEPROM to use the new tech lower cost with unique ID built in.
Oh yes, that's kind of, I just stumbled across that new EEPROM just the other day. So I just ordered some. I want to test those out too. But you guys probably have a tiny one. I've got a probably larger size package. But yeah, that's look. Actually, the one I'm looking at is actually twice the size of the original, but I'm not sure which. If you maybe just got the 512. Let's look at the 1,000 megabit. But yeah, so that looks nice.
So that says the ID is in the EEPROM, right? Not set by the user.
Yeah, I think that's right. Yeah, so it'd be interesting to see what people can do with that. I'm kind of curious. I don't know exactly how to use that. So.
And then there's a new FTDI part that supports USB-C. That was a long overdue improvement. Wow. Okay, Chip, maybe we can talk about your project. I have a picture of it.
I have a picture of it too. I just queued some pictures up.
At 2 p.m., I have to bail out to go get another notary for some government-related school purchase order things. Such a waste of time. So you'll be on your own with Ari.
All right. All right. Let me.
I don't know what you can tell about your project, your secret project.
Oh, it's fine. I'm sure Doug wouldn't mind. I mean, we've talked about it.
Do you have a circuit board picture handy? Because I have one of those.
Yeah, I do.
Okay.
I do. Okay. There we go. All right. First, let me go down to here. So here. So this is the board. Okay, I designed this for Doug. Now, Doug used to work at Parallax. He designed our ping modules, which we still sell a lot of. And so he has this company, Doco Engineering, now, and he's doing lots of industrial systems for window manufacturers and medical device manufacturers and all kinds of stuff. So he's consuming a lot of like PLC type products, and he's mostly in this Allen Bradley space where everything is extremely expensive and everything has to be kind of Allen Bradley compliant. They use a thing called Ethernet IP. So he wanted to make some kind of more economical board that he could use on his equipment and also sell as a separate product. So he actually called it the P2 Industrial. Turns out he was a big believer in the P2. So a while back, he went and checked out like half a dozen sites with the name P2 in it. Or he owns these URLs, or the site names anyway. So this is a board I designed for him. This happened really quickly and took a lot of hours, but this was about 6 weeks from concept to this finished circuit board. And I had to learn a lot about, IO, 24 volt IO that PLCs use, how to harden it to protect against, in PLCs, it's not just like you have a possible miswiring of it, like a possible ESD event or something like this. You can have like ongoing miswiring errors that could completely wreck stuff if you didn't watch out. So you see these green parts here, these are like PTC resettable fuses, positive temperature coefficient. So when they conduct enough current, they get hot enough that they open up. There's some kind of like, it's a carbon compound, almost like graphene or something inside, or graphite. And once that thing exceeds like a current range, it's not very exact. They're kind of, it's about about doubling is what your granularity is in current from maybe one device to another, but they provide protection. So they'll open up, and then they'll hold that large voltage across them and stay warm enough that they stay open. So you have to power the equipment down, then everything cools, and that graphite goes back into place, reconnects, one side of the fuse to the other. So when you turn it back on again, you've got a nice short there in that fuse. But if you ever exceed the current, it'll open up again. So we had to put a lot of that stuff in. Also, this black part here, that's a TVS, a transient voltage suppressor. So there's all kinds of like protection diodes and fuses and stuff, so that, if they completely screw this thing up and hooked up, 24 volt output to some 5 volt input signal, it's not going to damage anything because everything is protected through all kinds of these little fuses, and then through transient voltage suppressors, which can help open the fuses in miswiring situations. So anyway, we put a USB-C connector on this thing. That was kind of fun. And a little FTDI chip behind the connector. And here's the flash. We put a serial port on it for the next gen displays. There's like 2 Ethernet ports. There's what is this? A 5, a 3.3, and a 1.8 volt switching power supply. And then we used a big chain of these RGB LEDs. They're like WS2812s, but it's some other part. I can't remember the name, but they're like 1.8 by 1.8 millimeters. And you send them like a serial stream, and they all initialize when you finally hold low for a while. It's like a one wire deal. So it sends out to all those and then updates them. And so I've been working on all the software for this. These up here are like digital 24 volt digital inputs, outputs. So that's wired like 24 volts ground, and then the IO. And the IO can be biased high or low if you want to connect up PNP or NPN sensors. Or you can also drive. See this little chip right here with this big power supply cap? That's like a octal half bridge. So each one of those bridges goes to one of these 8 connectors. So we can also sync and source like an amp briefly or a half an amp at 24 volts continuously through this thing. So these things you could use them for sensors, for driving stepper motors, for sending higher current 24 volt signaling all over the place. And then we have 3. First, before we embarked on this, he had me develop a lot of jerk-based motion control code. So that's realized on the P2, of course, but then over these connectors, which take these, I think they're called clear path servos. And then down here we have 2 analog IOs that are like 0 to 10 volt in and out. I'm working on the code for that at the moment. This thing here is an IO link. So it's like a 24 volt 230.4 kbaud serial system that it's like ground, serial IO, and then 24 volts for the control load. And here's the ground for the control load. And then for the actuator load, we have separate, ground and 24 volts, because in these circumstances in industrial environments, you have lots of wiring involved in there. And when you're running higher currents to run actuators and stuff, you have significant voltage drop over those wires. So you need like separate leads for what is the control circuitry and what is the load circuitry, that might be umpteen watts maybe. So there's a lot of like what you wouldn't see in small electronics. There's a lot of duplicated wiring apparently in these bigger systems because you have to accommodate all these voltage drops that can occur on higher current loads. Anyway, what I was going to show about this, I've got another picture of this thing. Let's see. Doug built a really nice case for it. He had one of his engineers design this. It took her just a little bit of while, and it's really cool. Everything is flush, so when you put the case on, there's the USB-C connector. These they're like Amphenol connectors, I think. These are some Molex for the motors. Anyway, they're all flush. It's real pretty. The alternative is like an injection mold, but that takes a lot of commitment, a lot of money. But he's got water jets and CNC machines, and it's economical at low volume for him to just make these cases. And I didn't design that circuit board with an exact case in mind. I just laid the parts out where they fit. Like you see these 3 motor connectors. These used to be all in line, but the trouble is when you plug a connector into this, the shroud of that thing is so big that you can't have these things next to each other. All these other little 3, 4, 5 wire things are different. Those are meant to be abuttable, but these things have potentially large bulky connectors that go over these things. So I had to turn every other one around in order to get the clearance for the connectors. And then I still had the indicators down here. So it all worked out. But what I was going to show about this is there's this one little thing I had to do. You saw that there's, in all these little holes, there are those RGB LEDs, right? That you send this 24-bit RGB data to, and you send out to the first one, then the next one, and each guy captures what he got, and thereafter he just relays what's coming into the next guy. So it's not exactly like a serial chain where you think that the first one you load winds up being the last one on the chain. The first one is the first one, and then each guy passes the next serial string. So it's like a 1 wire in, 1 wire out. So it's a 4-pin device. Anyway, there is on this board, we had to do a lot of IO expansion because there's a lot of like signals which we need lots of, which are they can be high latency, like on the order of microseconds. They don't need to be like nanosecond tight, like the motor control stuff needs to be. These are signals that might control like the H bridge and biasing these digital IOs or controlling the mux for the analog. So we realized those over HC74, HC594s, and 165s. And so you can string those things together just like a SPI bus, and you can, send data out there. You set your data up, clock it, catch the data coming in on from the other side, and then just repeat that. Then when you're all done, you hit a latch signal, and then it updates everything at once. It captures new data into the 165s and then promotes the internal shift register in the 594s to its outputs. So I wanted one cog to be able to handle all that stuff and the LEDs and this H-bridge chip. But it became really challenging and took me a lot more time than I thought it would. But ultimately, what I needed was some kind of little state machine that can give me the next state for the LED output, right? So if you look at the bit protocol, it's a serial protocol for these LEDs. You have like a bit period it's like 300 nanoseconds. You want to go high, that means start. 300 nanoseconds later, you output your data bit, which is going to be high or low. And you do that for 2-bit periods. You do that for 600 nanoseconds. And then at the end, you have 300 nanoseconds of low. So there's like 4 equal bit periods, but there's only 3 states, right? Because you've got the initial high, you've got your data bit, which is held for 2-bit periods, and then you've got your what would you call it? The kind of clear at the end, a bit that has to go low so it can register the next high. So you have 3 bit states for each bit that gets shifted out. And then in the bigger picture, you're shifting out 24 bits of first red, then green, then blue data. And at the end of that 24 bits, which is 1 LED's worth, you pause, you hold low for like, I think it's 1.2 to 3.6 nanoseconds, basically 1 to 3, what would be normal bit periods. You just hold it low. And then when you're done, and then you give it the next 24 bits and then do a little short pause like that. And then when you're all done, you hold that line low for 50 microseconds plus, and then the LEDs recognize, oh, that's the whole frame, we're done. So let's all now update our parallel 24-bit, shift registers that we've been holding and promote those to the RGB outputs. So it's a nice little protocol. It's not complicated, but here's the trouble I had. That thing has a period all its own, right? Like not just the bit timing, but the whole mode of like, are we sending out a data bit? Are we in a little, post 24-bit clear period? Are we in a refresh thing where we got to tell all the LEDs to go? And this thing was completely incongruous to the shift registers, like the 594s and the 165s, because they have like a whole different schema, and the two things would never mesh up. I thought at first I could integrate them all, and I could do that if I really suffered a very low data rate on the serial to parallel to serial stuff, but I couldn't suffer. It was too all worked out. But ultimately, I realized that I needed a very simple state machine that I could call, and it would give me the next LED output state in a flag, like the Z flag, because the carry flag is already being used for shifting bits along that big data chain of the 594s and 165s. So I needed a way just to get the next bit into, say, the Z flag. That's why I chose the Z flag. So every time I call this thing, it gives me the next bit. And there's 3 states, right? There's that initial, what's typically an initial high, but that can become a low if you're doing one of those rest periods or the reset. Then I have a data bit which plays for 2-bit periods, right? That's high or low to represent data. And then we have another bit which is low. Always the last bit is always low out of the 3. So we play the middle one twice. But this allowed me to decouple the states between the shift registers and what the LEDs needed, because it's a crazy thing. It's completely enharmonic. There's no rhyme or reason. And I was going crazy trying to make it all fit somehow. But anyway, I realized eventually I needed I need a little state mechanism that I can go out and get the next LED state. Oh, and the way this thing works in hardware is down here is a 74 HC160, no, HC74, HCT74, because it's powered at 5 volts but fed by 3.3 volt logic. And what that thing does on the upstroke of the clock, we're sending data around the I/O expansion chain, right? Every clock rise, it's a new bit out and we get another bit in. But I made it so that on the falling edge, we latch the state that's going to the LEDs. So there's all this little hyper herky-jerky stuff going on that every time we drop the signal low, we have to output what would be the then valid LED state. Every time it goes high, we're dealing with the n-harmonic serial chain data that has like no relation to the LEDs. So here's this little thing I came up with. This took like days to get ironed out. This is the thing, see, the programming the P2 can drive you insane because the possibilities of optimization are just kind of like endless. And at some point, it's like playing chess or something. At some point, you just have to say, okay, I'm going to try to stop thinking about this. And I'm going to use what I got. And I don't think I can do any better than this. But getting to that limit is very soft. You know, it's not like you hit it and you're like, okay, that's it. There's usually something you can do to make it even better. So you see this thing here called the LED loop. You guys see that code? There is a register called LED PC, which actually holds the register location of what instruction it's going to execute next within all this, right? So it's initialized to this LED start right here. So that's the first thing LED PC points to. So what happens is every time the thing that's needs to get the next LED state, it's going to call the register LED PC, which is going to point to one of these instructions. And then what these instructions will do is set the next output bit for the LEDs into the Z flag and update the LED PC register so that when it gets called again, it's at the next state within this little state machine. So I had done all these things like, oh man, I got it down to 12 clocks. That's amazing. Well, eventually I got it all the way down to 6 clocks max. And so what happens is the caller does a call to this register right here, LED PC. It lands at wherever it's pointing. Like, let's say here it lands at this RF long. So this is where it needs to get a whole new 24-bit in the form of a 32-bit register. It gets a new 24-bit pattern that it's going to output to the LEDs, right? And during this time, the Z flag needs to be low. So you look at what happens in this little thing here. It does an RF long to get the next data, because down here, incidentally, when it started off, it set up the streamer to point to where the LED data is, right, where all those 24-bit values are. So it, right here, it gets, that takes 2 clocks, it gets the next LED long, or 24-bit pattern out of the streamer, puts it in LED RGB, then it writes, this $+1 means the next location, which is like the next instruction, right? As this assembles, it's going to wind up pointing to this instruction. So in one whack, it goes, okay, move the next address into LED PC, set the Z flag, or affect the Z flag. Now, because this is going to be definitely a non-zero value, that's going to clear the Z flag, right? So in one instruction, it points to the next instruction it needs to go to. It clears the Z flag, and it does a return. You paying attention, Ken?
Chip, quick question. What is this ditto thing? I've never seen that before.
What is the what thing?
Ditto.
Oh, okay. That's the thing we added a few versions back. It's like a macro. Well, it means repeat, like repeat generate. It's like a generate statement. So what it says is do this code 24 times. Make 24 iterations of this right in series. And you see this dollar sign thing? That is an internal variable. It's an assembly time variable, which cycles from 0 to n-1. So in the case of 24, it starts out at 0 and then winds up at 23. So it writes all this code out once with dollar sign equals 0. Then it does it again with dollar sign equaling 1. And then it does that until dollar sign equals 23. So it just creates a whole bunch of code, but it's all possibly different. I mean, you can use the dollar sign as the iteration, which is the iteration count. You can use that to make each little copy different from the other copies.
Okay, I get it now. Okay, thank you.
Yeah. So what this thing does first, it has to return a 0 because we're going to be low for a while, and it points to this next instruction. Then next time the guy calls LEDPC, he gets these two instructions. So this one is just this gratuitous way of generating a Z equals 1, right? Because if you move 0 into LEDPC and you say affect Z, it's going to set the Z flag to 1 because the result is 0. So that's going to serve the purpose of making that initial high bit that it has to output to the LEDs. And then it points to the next instruction and then does a return. So next time it comes in here, it's going to do these two instructions. And so this is where it actually tests the bit of interest in the 24-bit RGB pattern. It writes that into Z, and then it sets up the next address of where it's going to be, which is here, and it does the return. So next time in, it hits this instruction, right? Now this instruction has the job of, it has to leave with Z equals 0. And because this is non-zero, the Z flag, this $+1 is the next location. Whatever that value is going to be non-zero. So that's going to clear the Z flag. Then it's going to write that next location into the LEDPC, and it's going to do a return. So it's doing like 3 things in one instruction. It's like setting the Z flag to the appropriate value, setting the next instruction address, and doing a return. So in most cases, when you call this thing, you're only spending 4 clocks. And then it's going to do this. See, it's because these things are stacked up, it's going to do this 24 times. It's going to give you 24 RGB bits worth of states to output to the LEDs. And then down here, it does this LED iteration. How does it work? Oh, this will set the C flag if it's done whatever LED count is. I think in this case, like 15. So it's not going to affect, because the C flag will be 0 for most of the time it's doing this ink mod, because it's not hitting the limit yet. So it keeps returning C equals 0. Then only on the, so it's usually coming out with C equals 0. So this is always writing LEDPC to whatever it was +2. Now it's doing +2 because it was last left right here. Wait a minute. I know this thing's working, but that doesn't look sensible to me. Does anyone see a problem? LEDPC. Oh, because it only happens. Oh, wait a minute. Why would that not? It's always adding 2. The first time it's going to go to here. Wait, it starts off coming here. By adding 2, it's going to wind up down here. But in the case where you get a carry out, it's going to come all the way down to here. So this is like a conditional branch. But there's something, I know this runs right, but I'm kind of having some like misunderstanding about it at the moment. Anyway, it does it like for for oh, because it's either going immediately to here, or it's coming to here on the next iteration. So it loops. That's a way to get it to loop, to do all of the LEDs. So it goes all the way back up to LED loop here until the LEDs run out. Then finally, yeah, because it only comes in here once. It's not iterating in place. It drops in here once. So this is what the LED PC points to first. So when you add 2 to that, it's either going to be this one. This is in a case where you still have more LEDs. Then it sets the Z to 0, points back to LED loop, and does a return. So next time you're going to be back up at the top of this loop handling the next LED. But on the 15th time, when you're done, because the C flag was set in that odd case, and it's adding X, meaning add whatever this is plus C, it won't go here. It won't hit this. On the 16th time, it's going to wind up pointing to this, which then repoints the streamer back to the beginning of the LED data, and then sets up for the next location. And then this is really wasteful, but it's like, because time is more important to me than code space in this case. So 43 times 3 minus 1 is like, what's 43 times 3? It's like 129 minus 1. It does that 128 times. Is that right? And it just keeps this guy, see the ditto is being used to replicate this. So this thing just keeps, we're outputting 0 because this is the latch phase where you have to hold that thing down low for a really long time. So it just keeps returning Z equals 0 and goes to the next one, the next one, the next one. Finally, it falls out of that thing, out of all those copies, and then it comes to here. And it says, clear the Z flag again because we're going to output a 0, and now point LED PC back up to here. So so you can see that's the whole life of that little state machine. You just keep calling it, and it keeps giving you the whole bit stream for what all those LEDs need. And it only takes 4 or 6 cycles per call.
Yeah, Chip, I'm kind of curious, like, why invest all this energy into, because this is for like a WS2812, right?
Yeah.
I think it's max frequency something less than a megahertz.
Yeah, it's like, yeah.
So is the idea here to have this be inline assembly so you don't need a cog to drive it?
Well, yeah, I wanted to have one cog be able to handle the whole serial to parallel to serial I/O, like high latency I/O chain, and the H bridge and the LEDs, because I don't want to just burn cogs. Well, and see, I really had to do that because of the way I designed the hardware. On the falling edge of the clock, you're always updating whatever the LED state is, the LED bit stream state is. So those things were married. I couldn't put them on separate cogs because the cog that's raising the clock to run the serial chain is also the cog that's dropping the clock, which is then responsible for the LED states.
Okay.
Does that make sense?
And I'm curious, what frequency are you planning on running that device?
It's running at 200 megahertz.
Okay.
And there's like a bunch of heat pipes underneath the chip, and there's a big ground plane on the bottom, so it's kind of like a heat spreader. I mean, it hardly gets warm, but it was designed with thermal stuff in mind. And on the back side, I don't have a picture of the back of the board, but there are these little spark gaps built into the circuit board where you have exposed little tiny fingers that come within like 6 mils of each other to concentrate any electrical field if there's a big voltage buildup. So it begins an arc, which then, drags things. The arc will probably burn until you're down to like 20 volts or something, and then it will go out. And then, so it takes some of the burden of protecting the board off of all those other components, like the transient voltage suppressors and the fuses to a lesser degree.
Oh, that's interesting. I don't think I've heard of anybody doing that, but it seems like a good idea. Like if you get hit by lightning.
Where I learned all this stuff was ChatGPT. I mean, that thing, it's aware of so many different disciplines. It just told me like, okay, well, here's how it tells you stuff you have to evaluate. Is it sensible or not, you know? But
The only thing about that tracking thing, it sounds like if it did track, then I'm not sure it's recoverable on the PCB unless I guess
you mean
maybe,
what the tracker? You mean the arc thing?
yeah, because that's going to create a carbon track, right? So you have to dig it out.
It could, yeah. But I mean, here's the thing. Normally these signals are like 0 to 24 volts. So a carbon track's not going to be very conductive at those lower voltages. But if you get a big ESD event, you want to quash it without just relying on your little surface mount components to handle it all.
Yeah, for one thing that we use sometimes is these they're actual spark gaps. They're like uh maybe 10 millimeter long by 8 millimeter diameter, and you can actually mount them on a circuit board, but they can actually take like tens of kilovolts and
Oh yeah, and many amps.
yeah, those if you're actually thinking about getting hit by lightning, that'll work.
Yeah. This is not probably lightning proof, but and I mean those spark gaps are a little bit on the theoretical side, but I could see them helping. I mean, they would certainly start a conductive path to ground, and take some of the burden off of the TVSs and things.
Yeah, a circuit board version is definitely a lot cheaper, and probably I can imagine it working just as well. Yeah.
Yeah, I should have pulled a picture up of that. Um,
Yeah,
but
just
anyways,
wouldn't be
they're just little fingers that come together like this.
Yeah, the only question is how to clear out the carbon after it does track. But maybe just like a
But here's the thing, isn't the carbon path very high ohms, and it's likely to become a conductive thing if there's enough voltage? I mean, is it really going to conduct 24 volts with any amount of current?
well, you're counting on it to conduct all that current, aren't you? When it goes.
Oh yeah, when it goes, yeah, once the arc starts, the air is ionized and it's like a load, right? And so it's burning off all that discharge through.
Yeah, I think it's going to burn this. I think that plasma is going to burn the circuit board, and it's
It
going to.
will, but they are very brief events, right? They're maybe microseconds.
Yeah, maybe I don't know. I've never tried that, so I don't know.
I have a chip zapper that we used on the P1 to validate the ESD structures on the I/O pins, but it's this special thing from Switzerland, and one of the spark gap heads that plugs into it failed, and they wanted like $6,000 for a new head. I'm like, it wasn't worth it. But if I got that thing resurrected, we could actually evaluate, if those spark gaps are working okay.
Oh, maybe you could like cut the circuit board, like make a channel in the circuit board between the fingers. I don't know if that'd be possible. So it'd be just
Oh
air.
yeah. Well, yeah, these little fingers are like little triangles that point towards each other. I think there's like 4 of them. They come within 6 mils of each other, and then the solder mask has been cleared away from the whole area, right? So you see, oh, and also they go over they go over the selective soldering machine. So the selective soldering machine builds up those little fingers, with some solder that kind of becomes 3-dimensional then. So there's a lot of meat on those things due to the solder.
Is this like something that there's like written up design principles that guide how to do that? Or is this like just somebody did this once or
I don't know. Well, I noticed that Doug had given me a schematic of a product that he's using that he would like to, have his own in place of. And so I noticed these funny little, what turned out to be spark gap symbols on the schematic, but I was like, I don't see any component associated with this. And then I don't know I don't think I even looked at the board. I think I just asked ChatGPT, what does this mean? And it said, oh, these are spark gaps. And it said how it kind of gave the lay. Because so much has gone into the training of those LLMs that they know about just all kinds of arcane little things. And it kind of explained to me what the deal was with those and gave me some pointers on implementing them. And
Yeah.
so I just did that.
Yeah, I really like that idea. I'm gonna have to copy that one.
Let me see if we have other presenters. What I'll do is I'll go get a picture of the backside of the board, and then I can show it later. Anyway, that's kind of what I was going to talk about. That little state machine that's what you see there. That was like a couple days work to get it all. It took me a while to even figure out what exactly I really needed, but it just deposits the state into the Z flag, and it solves the problem of how to marry two dissimilar state machines, by keeping, the resolution of one super simplistic. You just call it when you want the next state, and then you use the middle state twice. Because I needed like a bigger gap in order to operate the latch, because that's kind of an exceptional timing thing, which happens only when you've like run all the data through the serial chain. Anyway, I'll close it. I'll stop sharing this thing. Now, Ari, what's next on the agenda? Is there anything?
The agenda went with Ken.
Does anyone else have anything they would want to present? Stephen, I see you showed up.
I don't have anything though. Got lots of things in flight, but nothing delivered yet.
Oh, okay. I got to show you guys something that Stephen shared with me. Let me find it here. This was crazy. So, Stephen's been using Claude, which is an AI from Anthropic, he'll like muster a bunch of these and Claude, what would you call them, instances, and have them work on things, because he's kind of applying his management know-how from HP to managing these AI things, which is sort of necessary because AI is only going to like apply a certain level of effort to some casual inquiry, right? So Stephen reminds it, I need you to be very exact, and I want all of you guys to do this. And so he kind of musters them and then has them do things. So they were actually able, the problem, the bug that we had in the quit next that I talked about initially, that bug was fixed, and I had to spend a lot of time kind of looking over the code to figure out, okay, why is this thing happening? And I realized that if we're, nexting or quitting out of a couple of levels, the intermediate levels before you get to the final one, they just need pops to be accounted for, that you have to pop out of the stack frame to get your context ultimately what it needs to be when you hit the final thing. So that's what I wasn't doing that in the case of the repeats. So anyway, it was like a real mind-bending kind of problem. But look at this. Stephen had sent me an email. This is so crazy. This is from my compiler, right? The compiler is written in 386 code, and it's generating spin bytecodes. The compiler was able, maybe Steve can elaborate, but it actually, you see this here? It's like the bug is here. I looked at that and I thought, what? Oh yeah, I guess that kind of would be. There was also another bug that it didn't really understand, that was this one. My comments became richer later, that we use a jump not zero here because it actually does an implied pop. But in case we're not at the final level where we're going to quit, we just have to account for that pop that must happen. So that it didn't figure that out, but it did figure out that in this other area, this is where the problem was located, which was kind of mind-blowing. And can you imagine looking at some code base that does some arcane thing that, and figure out, I mean, it took me 2 nights of staring at the code to kind of get confident enough to remember, okay, I know what I have to do now. But this thing analyzed it, and I'm sure it took Stephen time to present to the AI, what the problem seemed to be. And then the AI went in and actually looked at the compiler, and it was even analyzing like bytecode output.
It was really kind of fun, if I may, Chip.
Yeah, go ahead.
If you look at the forum thread, Bacca had reported on and showing bytecode examples and things like this of where he thought the problem was. And there were 2 other people that chimed in the forum saying, here are the symptoms and things. And so the way I approached this was I downloaded the latest copy of the source for Pnut that had the problem. And then I put Claude in there studying the source. And then I gave it all the feedback from the forum of what the different members found. And I said, here's what it seems to be finding in terms of what the problem is. Can you assess if these reports on the problem are the real problem? And do you see anything else with it? And that's pretty much the approach I took. And then this is what it came up with as a solution. And as you saw, there was no evidence. I'm guessing there wasn't much evidence of the second problem, and maybe that's why Claude didn't look deep enough. But I don't know why it didn't find the second one. But I'm very pleased that it was able to confirm where it thought the problem was based on the symptoms reported.
Yeah, if I had put the comment in there that we're using this jump not zero because it does an incidental pop, so we don't have to account for the pop discretely, it probably would have flued in and realized there were 2 places that needed help, not just one.
Mm-hmm. So it was, I'm finding that I'm using this technique a lot to ratify what people are telling me that I should look at. And then auditing Claude's impression of what it thinks the issues are against what I think the deliverables should be. And so even though Claude comes up with answers, you still cannot trust it entirely. It's only another opinion. And so as long as you're careful to treat these as opinions, and then ratify everything yourself, working through the logic, you'll have good results because it'll reduce the amount of search time for sure.
Yeah, it's kind of like a brainstorming companion that is willing to do some strange, difficult peeking and poking around. You might not be inclined to do, and it might help you out.
Like randomly staring at bytecodes and figuring out what they do, and staring at 8086 code. That I don't know about you guys, but for me, if I go back to 8086 code, it takes me hours to get back into context. And Claude doesn't have that issue.
Right. Yeah, it took me 2 nights to feel confident enough to know exactly what needed to be done.
Right. Now, the other side I found is that Claude's able to, I didn't hear from you, Chip. Were you able to did the regression test source file that it created, did that actually exercise the problem that you were chasing well enough that you could prove it was fixed using that code?
I only used Mac. I didn't really try that.
Okay.
I just used Mac as example that he had posted on the forum. But I mean, I realized where the problem was, what it was about, and then so I'm pretty confident that I totally fixed it and everything is accounted for. So I didn't.
Excellent.
So it passed his test just like his compiler did. So I figured, okay, that's probably
got to be pretty good then. Yeah.
Yeah.
Well, I'll be using. I use these same techniques now to audit your changes against the existing Pnut TypeScript, and then the difference is less trust has to be involved in this case, because I take your code, generate the output files, and I have regression tests that I run against your code and then run against Pnut TS, our code. And if they match, our compiler's good. And so I don't even have to trust the AIs anymore, except for to do the work and make sure all the regression tests run. The good part is I can use the AIs in concert to run through and expand the regression tests and run them against your compiler, run them against the combined R compiler. And if they get the same results, we've just increased our regression testing coverage. And so I am using AIs to improve our coverage, which is a fun thing to be able to do. You know, it's much less, you know how painful it is trying to get good coverage and trying to generate coverage tests and think through what instruction sequences we need to cause regions of the compiler to be exercised. And it's not as painful using the AIs, which is quite nice. Especially exception testing. That's a nightmare to try and figure out.
Oh, yeah.
And
Yeah.
now I can generate 10 or 15 tests. The hardest, the longest timeline for me now is running each of the failure cases by hand with Pnut and then renaming files so I can use them in regression testing and then running our compiler again. And so I should be darned happy, my opinion, that that's the longest thread now.
Yeah.
In terms of workload. So every release, Pnut TS gets stronger and is verified more accurately against Pnut. We've got 100% coverage of all the assembly language code generation now at this point, including effects and things and conditionals. So
yeah, that's good.
Much stronger. And my turnaround time went from months to catching up with you to days now, which is just stunning. So I used to be worried about you being too prolific with these changes. And now I'm just excited for you to do what you need to do, and I'll stay caught up with you.
All right. Well, as I see needs, like working on this stuff for Doug, you know, I've added a few things to the compiler, like Indian instructions and other stuff. But the more you do with the chip, the more you realize the tools could, you know, morph to make other things easier.
Absolutely. And that's what makes that's what makes the spin and the PASM really fun. So yeah, I'm excited. And if anybody's noticed, there's another forum post about how to interact with the P2 knowledge base interactively from your command line. And so now you can use three different AI agents, Cursor, Codex, and Claude Code. And by adding this tool alongside of your installation, they immediately have access to interactive search with the P2KB. So they can now dynamically answer questions about the P2 architecture, PASM2, and SPIN2. So that is just fascinating.
Yeah, I think that's the ultimate application, is not necessarily a manual, but an interactive helper that can kind of just guide you into how to think, what you need to be thinking in order to get to where you want to be.
So it's common for me now to sit down with a new piece of hardware and want to add code for it. And common in that I've done it 3, 4, 5 times now myself. And I'll sit down with a new piece of hardware. I'll locate the data sheets. I'll tell it how I have the hardware wired up, it being one of these agents. And then I remind it that it has access to the P2KB, the P2 knowledge base. And I said, okay, I have this new hardware. What kind of features can we use to do a really performant driver? And so one of the cases I had was an 8x8 sensor array that is driven by a SPI switching interface between the 64 sensors, and then analog conversion, because they're all analog sensors. And I was able to get the frame rate up to 1,300 frames per second by using techniques that the AI agent was able to help me with and program the P2 to get that performance up.
That's good.
And so it works. It works in a very stunning fashion. So if you're excited at all about playing in this area, my role right now is just providing tools that make it easier to do so, and then continuing to improve the Spin 2 environment, the extension for VS Code, and the TypeScript compiler, and then the downloader debugger as well. So I'm using the tools daily, and I'm working to improve them and release new versions.
Super. Well, we can talk about anything you guys want to discuss. You're all welcome to share what you like.
Did you dig up that graphic or PCB image of the?
I've been talking to
you know what? I got all excited. I was thinking about AI here. Okay, let me find it.
Sorry, I hooked him.
I wanted to say hello to Steven Morocco. It's Martin. How you doing, buddy?
Hey, Martin. Good to see you.
Good to see you.
Yeah, I'll be looking for it here and see. This email program, what is Outlook? It seems like it's gotten very hard to navigate. Like I can't find my folders, and if I go to view, it should allow me to see my folders, but let's see. Okay. Let's see.
Yeah, I'm glad to see a USB-C board coming, at least for P1. Hopefully you guys in the future will get a USB-C board for P2 going. Maybe it's a minor thing, but it seems like that's the future to me. So I like to see it.
Yeah.
If it's okay, I have a question for Stephen and perhaps Chip.
Yeah.
In my work, I've always just used FlexProp, and partly because that's what I started with, and partly because I use some of the C library that he provides. If I were try to move to switch to Pnut TypeScript, are you guys able to access C and C libs at this point?
That would be a no, huh, Stephen?
Correct.
Yeah,
Correct.
just
we don't have that
spin,
interface built in. That's why you want, and John just texted, and he's right, John McPhalen. It is only canonical spin and PASM 2. The going from our direction to FlexSpin is nigh unto impossible if Eric chooses to change how he interacts. And so the right tool answer, if you're going to mix languages, is to work with FlexSpin. If you're going to, the whole point for Pnut TS was to create a Pnut or a Propeller tool replacement that is cross-platform. And so it wants to be 100% compatibility with those, and that's our goal. We also added deep regression testing. So any changes we make, we can't go backwards, if you will, in terms of compiler code generation. So it's a strong framework, making sure the technology lives on as the language develops, and making it maybe, I don't know, Chip's really fluent in working in the x86 environment, but I was going to say maybe making it a little easier to maintain. So I don't know. I think Chip would say his environment is easier for him. And I would probably say that the TypeScript is easier for me for sure. But
the 386 is a pain because you have to be very conscientious about what registers are doing what, and you only have a few of them. So it's difficult. I mean, I kind of just wish the whole thing was in spin. That would be nice.
Intriguing.
So does Peanut TS work on a Mac?
Yes.
Okay.
And it works on Raspberry Pis, Linux machines. And so, yes.
Because I hate Windows with a passion.
I'm right there with you. Sorry, I'm a Mac guy since 2011.
So then just one more question, and I
Please.
thank you guys. The thing right now, I believe the only reason I'm using C is that Eric provided drivers that have been very reliable for the SD card on the Edu module. Do you guys have that for the Peanut TS side? Drivers for the SD
You'll
card?
find that's what we call an excellent question in HP parlance. Excellent questions are those for which we already have an answer. Okay, so I'm actually investigating releasing a triad of drivers. And I'm about to release the SD driver that you're talking about.
Great.
I'm in final testing right now. Only one other person has even gotten close to looking at it. It's purely spin 2 and PASM 2. It's using the streamer and the smart pins, so it's trying to get as performant as it can be. And it gives us formatting on the P2. It gives us FSCK on the P2. So if you think you've damaged the image on it, you can tell. It was also an adaptation of one of the forum members in 2003 created an object. He joined in 2003. That's not when he created the object. What's his name? Chris Gadd. He created an SD driver for the P2.
I tried that and I couldn't get it to work.
Correct. And so what I found was there's interchange issues in 3 different locations of the drivers that he just didn't need to pay attention to for his use. And so what I did is I took that driver and Ray Allen has a port too that John's reminding us of. I took that driver and identified all the issues with interchange between the different operating systems, and then organized the write operations for better power down failure recovery. And so now, if we lose power, there's more chance of your data not being corrupted on the driver. Having made all those changes, I also moved it to a backend cog, so 7 cogs can access files simultaneously. That being done, I added a full regression test suite and performance analysis, and also adapted the driver to study the controller that actually lives on the SD cards. And each controller recommends its own timing and weight and everything else, and has different performance issues. And so this now adapts to the performance of the SD card. And it's fun to watch it interact with different vendors' cards now. I haven't found a card I can't use with. The most problematic cards are PNY, but the driver sees that it's PNY and notices the erratic behaviors of the driver and just handles it really well. It does detune its performance because the PNY controller chips are different. I'm playing with Gigastone, Lexar, SanDisk. I've got a whole catalog of cards I've already tried, and I'm getting excellent performance. And it turns out the Lexar cards are turning out to be the highest performant cards we have out there so far.
Which cards?
Lexar.
Lexar, okay.
Lexar. And so I have a full, in the driver release that I'll release, there's a card catalog of cards I've tested with and the performance I'm getting. So this is a certified driver, all the robust regression testing it can do. You have directory handles, so each cog can be at a different location on the SD card. You have file handles, so you can have multiple files open. You can compile time and choose how many file handles you want to support. So if you need to make your in-memory structure smaller, you can. There's raw sector and register access that needs to be available. And that is conditionally compiled out unless you're compiling the formatter or the characterization tools or the or the repair tool, file system repair tool. So this is all going to be there.
Sounds fantastic, because what I was doing was getting something really simple working. I'm using 8.3 file names, which is
I mean, this is the limitation there
terrible.
too. Yes.
But yours will fix that limitation, right? Or not?
No, I haven't put that feature in. I could.
Okay.
We
I
could
mean,
put long file name in. I haven't put it in for the first release.
or even directories would help, because right now I'm just flat.
We have full directory support at any depth you want. That's all there.
That's great.
Now, Ray Allen is telling me that Evan H has an improved driver, and John is mentioning you Ray's driver. So it's going to be fun. I'll take a look at those drivers, but my point was I wanted something that was entirely PASM or Spin 2 and performant. Now, why am I going my own driver? The next release is integrating the flash driver with it. So if you have an edge card that has the MicroSD, and these will be independent releases, the MicroSD and the flash chip, you now can copy files between the two and things like this. So you can, pull out the card, put in the card, copy files over, pull the card out, and continue working.
I'm doing that programmatically now.
Exactly, and that support's going to be in
and
there.
it's I have to shuttle things through the processor using my own spin code. It's not great.
Correct.
I look forward to the release of this.
That's
Yeah,
coming.
I have to say one thing though, is that the one in FlexProp is based on I think it's FAT-FS, which is
Yes.
it's like basically like universal, like it's been tested on like almost all microcontrollers. So
Okay.
I think in terms of reliability and stability, it'd be difficult to beat. Let me just say that.
Well, yeah, my goal is to try and make one that we have a driver that we can. I'm not trying to replace FlexSpin's driver. For someone that wants to use and stay with those tools, I don't have an issue with that at all. I'm providing an alternative that you can build into embedded system that doesn't require that compiler, and therefore that we have these tools available.
Well, and it could be too that I think that the way the linker is working, I'm generating a lot of code in my executable by bringing in C. And
Yes.
I would guess that if I'm able to use a pure P2 PASM, I might be able to save some memory, some program memory.
Yes. And yeah, that's generally true for many different architectures. There are cases where I'm going to run experiments and I'm going to stay in C and use FlexSpin. There are cases where I really want to be native PASM and be as tight as possible. But my goal is I want a set of drivers that allow me to use all the edge card facilities in a single driver if I can. And so the 32 meg with RAM will also be supported. And you can choose to use a file system based driver on top of that RAM if you wish.
I'm not even sure which driver I'm using for the PS RAM at this point. It's working well. I'd have to look at my code.
Yeah, nice. So my goal is to provide a trio of drivers, and you can select the mix of drivers you want. They'll just be available for use. And the goal is to make sure that we have exhaustive regression tests on all the drivers. And anytime anybody sees an issue with them, we just add to the regression test and make the repairs. And then it's that much stronger from there forward. So I'm just trying to do a universal set of certified drivers like we did with the flash file system. And same level of testing, same level of certification. And people can choose to use them if that's the right thing for their project. There's no suggestion. FlexSpin will be the right thing for your projects. MacOS tools will be the right thing for your projects. Sometimes these will be the right things for your projects. And so I'm not trying to corral anybody or direct anybody. I'm just here to provide more choice.
Yeah.
Things that I'd like to use on my projects in the way we are. Having the hardware and not having a certified set of drivers and watching the community flounder for a while, and finally they rallied. And thanks to Ray Allen and Evan H. and Eric getting the drivers in the compilers, it's not been as rough as it was initially. But I still feel the need to fill in a couple more holes here, and that's what I'm trying to do.
Thank you. Very helpful discussion.
You're welcome. Thank you.
And just to be clear, that FSR W1, it's not really mine. I kind of just took it over at some point. So
okay, I hear you, Ray. Thank you.
Yeah, thanks, Ray.
Ray, you see
There we
this?
go. So you're not putting little ghost icons on your board, huh? Those are really lightning protection.
Yeah. See, this is the ground plane, right? All this area is the ground plane. So some of the fingers attach to the ground plane and the other ones go to the pad that, attaches to some external signal. And then so in some cases, like here in the motors, we actually, half the connections are ground and then half are signal. So we just do it like this.
I'm gonna have to search up and see if there's some engineering webpage that has like predetermined like how to distances and stuff for certain voltages, or if it's just all winging it.
Well, even at 6 mils, I think it doesn't really arc until you get to like 300 volts or something. So it's way, way outside of what you would normally encounter. But you can just ask ChatGPT. I mean, it has absorbed all kinds of stuff that was written about this in the past and the trade-offs of doing it differently and the gotchas, and it just kind of gives you a pretty good report on, how to arrange these kinds of things.
Chip, without solder mask underneath the teeth, do you have to worry about bridges when you're doing the, selective soldering?
I don't think so. We're going to find out, but I don't think so. Because the board doesn't have, I think, much more affinity for solder than the solder mask does. The FR4 underneath. I think the reason that it said to pull back the solder mask was that you want some kind of like 3D, third dimension in this thing, where you want those little points to be elevated and pointing towards each other. But then when it runs over the selective soldering machine, it's going to deposit definitely more solder onto those things and build them up, which could initiate the arc earlier and make it probably last longer and provide a higher cycle life because you're not going to be just chewing through this thin copper. See, I had to put some of these at an angle because of like these kinds of feed throughs right here. But in other cases, I was able just to do it, whoops, just straight like that.
Well, that's a very interesting idea. I'm definitely interested in this. I'm gonna have to, because I do work with a lot of high voltage stuff that can get that gets destroyed a lot. So this is a very interesting idea.
Yeah, I was looking at pictures. I searched this just to do an image search, and you could definitely see it on like HVAC controllers, that are dealing with long wire runs. They would have like really beefy versions of this on their board. I didn't have lots of, room, but I think this should be sufficient for what we'd be looking at anyway. But the crazy thing in PLCs, you don't just have to worry about this. You have to worry about them completely screwing wires into the wrong places. So even like the 24-volt outputs are fused with half-amp PTCs. So if they just connect 24 volts to ground, the world doesn't end. And also in an industrial app, you really don't, there's they stick these things into cabinets, and it would be really inconvenient to, have to go get a new one or make a repair. You want the equipment to survive and be able to kind of cycle itself with power and kind of reset itself so that you can run it again without having to, get into too much of a fiasco. Spark gap, I think that's the word.
Well, it's kind of interesting if it would be, it might initiate as a spark, but I imagine most of the current will be on the surface of the board once the, uh, I think that's usually how it works. I think that it'll initiate as some plasma and then it'll move to conduct on the surface of the board. That's why I think it's probably going to carbonize if it really got hit hard.
Yeah, no, I could see that. I think though, these kinds of events, you might have to survive, I don't know, half a dozen in a product lifetime, if that. And they would carbonize at FR4 a little bit, but I think those paths would be high ohms under regular working conditions and probably wouldn't amount to anything.
Yeah, well, I work in a different world of pulse power where things uh, they get carbonized really badly. So yeah, but maybe it depends. Like, it
So
depends on
they're
how hard it gets hit.
so they're seeing a lot of high voltage events then,
Yeah, yeah.
because only arcing is going to cause this carbonization, right? Or this plasma is going to burn stuff around it.
When I worked in the golf course industry, we had a huge amount of protection on outputs that go from a sprinkler controller out several hundred feet of wire across the fairway of a golf course to a big golf sprinkler head. And so even then, there were times when, after a bad lightning storm, you could open up a cabinet and the inside of the cabinet looked like an Art Deco project because all of the components had been vaporized by the lightning and the metal from the components deposited on the inside of the cabinet.
It's like those two wires way out there were just one half of the circuit.
It's
Wasn't
a
like there was
giant
any.
antenna, a
Yeah,
golf course
yeah,
irrigation stuff. It's yeah, tricky.
yeah. In chip design, you can't have too long of metal runs that don't go to some diode or something because of antenna effects during plasma etching.
Yeah, so we would the controls part of the circuit was generally optically coupled to the output stage so that the expensive part, the controller itself, that had the microcontroller and the displays and all that, generally fared pretty well. But the output stages were almost sacrificial the way that we made them, because if lightning hits a wire on a golf course, there's no protection at that point.
No, no.
It's just minimizing the destruction.
Yep. Yeah, I could totally see that.
Yeah, I had one board recently that had a I2C IO expander between the wires of interest and it was a P1 chip, and I thought that I2C thing would protect me, but no, that thing exploded and it just arced across and it took out the P1 anyway. So yeah, it's definitely good to have some protection things in there sometimes.
Yes, I got to show you a picture. Let me see here. Okay, let me share again. Okay, here we are. So you see this here. This is the H bridge, right? There's an H bridge in one of these caps for every set of 8 of these. So this cap is to trap like back EMF and things from inductive loads and kind of quench it to the positive 24-volt supply. And all these circuits are going to be fed via this Schottky right here. So this is like a 40-volt, maybe it's even a 100-volt Schottky, but it's got low forward voltage drop, but it can pass a lot of forward current. I mean, for what's on this board, this is way overkill. But what was happening, I got these little micro grabbers. I mean, tiny, tiny. They look like little, pincers on the end of a beetle or something. They're really small. So I could go and grab, do you see what I'm pointing to, this H-bridge chip? Can you see my little white cursor there?
Mm-hmm.
So that chip is kind of dangerous to use on a circuit board because they'll have like a 24-volt supply input next to a 3-volt digital signal. So what I was doing is I would power the board down. I would put the probe onto those pins because I wanted to make sure that I was signaling the chip correctly because it has its own SPI bus, right? It's talked to by the same cog that talks to the I/O expansion stuff and the LEDs. But anyway, it has its own pin. So I wanted to see that I was signaling it right. So I turned the power off, put the clips on, make sure that they're not shorting to any next door pin that's like 24 volts. And I'd watch it. Everything was fine. And then I went to do some more testing and the thing started breaking on me. It's like, what happened? Doug came by and he goes, well, is that cap storing any charge? Well, think about that Schottky there, right? 24 volts on the anode, 23.8 on the cathode, going to that giant, like, what I think it's called electropolymer, that cap there. It's a 100 microfarad cap. And sure enough, I powered the board down and stuck a probe on there. That cap was at 24 volts forever after the power went off. And I think what I'll do in the next revision, I'm going to bridge that Schottky with like a 10K 10K resistor so that it can handle any transient back EMF from the loads out on those digital IOs. But when the rest of the board draws the 24 volt supply side down, it'll pull that cap along with it rather than just have some cap that goes always to ground, so you're always burning power. I think I'll just bridge the Schottky because that thing is like, now it's, you turn the power off and minutes later, there's still 20 volts on that cap. So what happened was, as I was manipulating the little prober things, the little pinchers with the power off, I didn't realize that I was, 3.3 volt pin right next to one of the 24 volt supply pins. And so it not only blew out the pins on that H-bridge chip, it took out a section of 4 pins on the P2, which is a real pain. I mean, it's funny that we happen to have the VIO is for every 4 pins on the P2, right? Every set of 4 pins has its own. So there was one clean block that completely ran the SPI bus for any number of those H-bridge chips. And that block is what blew out. And I thought that was the case, and I confirmed it by getting a little thermal camera with the macro view. And I could see it was like 102 degrees right in that corner of the chip, right here. See, those are the 4 pins right there that attach over to this H-bridge. And sure enough, there's a hot spot on the thermal camera right about there, right where the die is that supports those 4 pins. So we have to, if we're ever going to resurrect that board, we need to replace the P2 and the H-bridge, but that is a really messy proposition because you have to get so much heat to get that tab off of the P2 that you're probably going to melt the switch, you're going to melt these connectors. There's going to be a lot of melted stuff afterwards. And,
yeah, that'd be a situation where having that industrial P2 device would help. You just pop it out, pop it back in.
Yes.
Back in the game. And that circuit with the cap and the Schottky, I think it sounds like what you're describing a snubber circuit. Is that right?
Right. Yeah. Well, it's so that the way I look at that circuit, it's so that when you get back EMF on the H bridge, it can dump. It's gonna have the effect of lifting up the 24 volt supply that the H bridge uses. So by having a capacitor there, it can collect that charge and then feed it back later under other sourcing loads.
Yeah, I think the general term for that is snubber.
Snubber, yeah, definitely. It's meant to control voltage rise or to limit voltage rise by just putting a big cap there.
And I'm trying to remember, I think in terms of de-escalating the voltage. I think sometimes you put a coil. I could be wrong about that. I think sometimes you put a coil around the cap to drain it, but I might be wrong about that. I haven't looked at that in a while.
Yeah, we just did what the data sheet advised.
So you're I see it looks like I'm seeing 3 power supply circuits there. Are they like, is that like meant to be just to get the total power you need, or is it like a redundancy?
Yeah, they're 5 volt, 3.3 volt, and 1.8 volt.
Oh, they're all different voltages. Okay.
Yeah, so some of the stuff like the motor signaling is at 5 volts. The LED signaling is at 5 volts. The P2 and the Ethernet chips and most of that expander logic is 3.3 volts. And then, of course, the core of the P2 is 1.8. Yeah, see these, oh, you can't see, see on the upper right? Those are like wire screw terminals that plug into these kinds of connectors. And they're sidewise, they're kind of like flush. They don't creep over, so you can put those things together very tightly. And I'll stop sharing this.
Yeah, the only thing that I guess I'd say is that H bridge is very close to the plastic. So if you did have to change it, I guess that would, yeah, it'd be a little tricky to change out the H bridge chip.
Yeah, it would be kind of messy. I think for this board, we'll just, I can still do development. I can't prove the sink and source on those bridges because that's broken, but I'm still using it to get the analog all ironed out.
Hey, Skippy.
Yes.
Doko provided a video where you're controlling a gantry with that. I don't know if you showed that or not.
Oh no, you want to show it?
It's really cool. Yeah, I just saw it in my email, so let me just paste it into the chat. People could watch it on their own if they're interested. Looks like it's your test setup.
Let's see.
So I put a link in the chat.
Oh yeah, here I can, here I'll share it.
The trends.
Let's see. Why can I not? Oh, here we go. Here we go. Hold on. Oh, let me just hit the link again. Gosh, where did things go? Okay. There it is.
Here's the trends. So you can see what the trends are.
There. Thanks, Ken.
Fun to see it running.
Oh yeah, it's pretty neat. It's been fun to work on.
You
Sometimes
really,
the hardest thing though, sometimes Doug wants me, okay, we'll get it to this stage. Well, it's like, it's really, I have a very hard time moving forward before I feel like I got the foundation right. You know, but sometimes he just wants, like, I got to show somebody something, or we got to have this guy do it now. And
yeah.
The last time I saw somebody push you so hard and get results was in 1997. Steve Long with the SX key debugger.
Oh yeah.
Cute.
Yeah, well, this will be maybe the first job I didn't get fired from.
If anybody's interested, I have some initial performance numbers for the driver.
Sure.
MicroSD driver. I want to see if they seem like they're in line or not. Everybody see these?
Yep.
So this
they're so tiny.
This is the Lexar card. Are they tiny for you?
Yeah, but I think it's, how can I?
How's that?
Okay, yeah, we just have to make it. There's some things we can press here, like what controls do we have over
I could
here?
adjust the page. That would make larger. That would make it larger.
Oh, go to standard view. That puts it in the middle, and then puts all of us up at the top.
Okay. So does this, Ray, you have experience with the drivers. Does this look reasonable, or John?
Ray, you there?
I think Ray had to leave.
Oh. So this is what I'm getting with the microSD driver. And to look at, since we run the SPI at this speed, and that's calculated from our clock speed to some degree, I also ran the numbers at 270 megahertz. And you can see the Lexar card is still performing quite well. And so, well, let's see, what other cards do I have here? Here's a Gigastone Camera Plus. Looking at the performance rates, not as fast as the Lexar. But this is me doing timing to make sure the driver's working and running the regression tests. I'm delivering the tool that generates these. I'm delivering that tool that calculates that to anybody that wants to use it as well with the driver. So you can check your own cards. So I think I'm getting reasonable results. These seem to be respectable. I'll try and run some comparative tests later after I get the driver released. Anybody have any questions? All right. Just to let you know, they'll all be published at the website with the driver, so you'll have access to it with all the different cards I test.
Are you looking at the classes on those SD cards when you're doing them? We use a SanDisk 16 gigabyte class 10 card in most of our products.
Oh yeah, let me show you that to give you a sense. What am I studying?
Stephen, I may have missed something while I was out, but are we micro SD card driver?
Yes.
You've taken that project on?
I'm about to release it. And so, yes, you're asking me what I was doing.
Okay, sorry.
No, hold on. What do I want here? Which is the one that looks like it's the one? Tell me if that's the right share. Okay, I shared it differently this time, so it's just the window. So SD card catalog, this is all the cards I'm testing, but this is what I'm using from the device interface. So you can see the informational and used. And then when we come down here to look at the cards, here's the summary table of the cards I'm testing. And yes, we're testing all different kinds, all the different speeds. And so these can show you how the cards are characterizing. And then this is some early throughput. This may not be my current, but it's pretty close. I think I've updated this. So you can see what kind of crazy range we're getting. The P and Y cards.
Man,
down there.
The speed.
Yeah, versus the Lexar cards, which is way up at the top. And then you can see the SanDisk show up, but not as performant. And then there is a SanDisk that's higher. And so all the details for these cards are here in this detailed list. I even pulled in some industrial cards, thinking that we might have the access to higher than 25 megahertz on the SPY clock. And yeah, nope, not for single wire. It's a dream, but nothing. Every one of the cards that I used pulled in, including high-end name brand that I use for my drones, just don't work. Let's see here. Do I have any more? All of this is going to be delivered with the driver. So what am I getting here? Yeah. And so when I'm testing speed results, do I get performance? So I'm testing, do I get any failures at speed? And so I'm literally checking everything. This is the Lexar card. If I'm scrolling too fast, just stop me, please. Read timeouts, write timeouts.
Hey,
Files.
Stephen,
Please. Yes.
did you say that PNY? I can't believe it's that slow. It's just that slow in the SPY bus mode, right?
In the SPY bus mode, correct.
So I'm
Single
sure
wire SPY is that slow. They have some really strange drivers. By drivers, I mean the controller on their card is really strange. And so I get huge variance. I don't see, can I find this? Can I find this in this page? I wonder if I put the notes in here. It is stunning, the effects I get. I wonder if the notes are in here. There's a huge amount of variance. Here, what does this say now? I don't think that's true anymore. I was able to certify that it works up at full speed, the 25 megahertz. Since we're using the streamer, you have clock rounding, so you can't quite, depending on what clock speed you actually choose for the processor, you can't quite get to 25 megahertz. And going over is a bit problematic. However, if I can go over to achieve the 25, the driver would select that. We're using the streamer and SPY, so it's highly performant. This doesn't have the information I was looking for. There was, yeah, right. Well, this is one of them. It's crazy silly. The 85 times slower than other cards.
it's a wonder it even kind of works. I mean, you must be talking to it at the SPY bus speed of 25 megahertz. It just has a super high, like slow response period to you, right?
Correct. And so I had to work with a driver to get it handle the range of response rates and things like this to make sure it was really stable with all the different cards. If you do any research for the PNY brand, there are all sorts of rumors about how people had to interact with the card to keep it working. And it's like, because lots of things under normal behavior don't work. But this has been working well. You know, I pick up a card, you characterize the card, the driver adapts to it, and then you can run with the card. So I don't have a card on my bench now, and I've got some China clones. There are SanDisk clones from China that don't say they're SanDisk, but the controllers are SanDisk derived, so they're probably clones, not really SanDisk, but they're signing on. The controller is signing on as SanDisk. But they're much slower. Yeah, so you can see I ran at 25. Accurately reflects, so the register itself is actually accurately reflecting the card's capability. And so, yeah, I tried to do a lot of, we are treating, this driver is running with full CRC turned on. And so all sectors, readback and writes are with CRC generation, and readback is CRC verification. And so I know if I'm having any bit drop out to and from the device. And so these speeds that I'm measuring here on these layers that I've showed you are with full CRC support enabled. So high data reliability is the intent. So I think from what I can tell so far, I think we've got a good driver.
Looks good.
But a lot of cataloging, a lot of trying to understand what the issues were. P and Y did not come up right away. All the other chips came up, and P and Y just wouldn't. And so I ended up doing research to figure out why. And it was the variance in how the controller behaves.
Gee whiz.
Was
They
Claude
probably
helpful?
just designed that thing to run USB 3.0 or something, and this was like a afterthought, barely getting it working.
Yeah. So yeah, full regression tests, checking everything, all the edge cases, trying to do data throughput, characterization, trying to do, I built the thing originally without CRC, and I said, wait a minute, why? I said, let's turn it on and see what you can do. Oh my gosh, it had no end of. We ended up using the CRC polynomial instruction that we have built in to make it all happen. So thank you, Chip. That was fun. Although discovering the polynomial and how it actually worked the way the sectors needed it to see it actually took a whole bunch of iterative code building.
Oh yeah.
You read the research papers, and it's obviously going to be this polynomial, but what's the seeding? And you get 3 different seeding suggestions, and it's like, which one works? And so
right.
We spent a bit of time trying to figure out which ones worked, and finally found it. But fun work, because it's proving that I can do this kind of work. And this is all with the AI assisted P2 code development. So yeah, pretty cool.
Yeah, you have a good how can you say it? Like, your brain is around this pretty well. I don't think mine is so well. Other people's probably aren't either, but it's a hard thing to know how to do. I mean, it's probably not that hard once you're in it, but it's probably a big impediment is realizing what it can do.
What aspect are you speaking to?
Well, just you're pretty fluent in how to use AI to get all this kind of stuff done.
Okay, yeah. I have my days where I'm bitching at it, like all of us.
Yes.
But I have a very different success rate because I've built some tools around it, some tooling that allows me to do long horizon development with the AIs. And what I mean by long horizon is all of us have experienced asking things to the AI, and you'll work for half hour, 45 minutes, or an hour, and eventually, what do I want to say? You get to, it has to auto compact its conversation.
Yes.
And depending on which AI you're using, some of them are getting better surviving that. All of them are equally kind of still bad. And so I have tools wrapped around that provide that memory through that event. And so for me, where other people, it's a couple minutes repopulating the history of what's been going on and trying to get it back operational again. Within a minute, I'm fully operational and back in full context. And so I don't suffer those events anymore, other than I'm anxious and I'm working and I'm fast and auto compact happens and there's a 2-minute dead time. So all of your mental processes just stop going, okay, let's just hold here waiting for me to tell it what I want to do next because it's not listening, that kind of thing. But yeah, I'm much more fluent now because I have those tools available. But the P2KB, I've been doing 5, 6, 7 different P2 projects now. And the first couple stumbled because the information wasn't organized well, or there was bad information in the database. You know, how we first started, it wasn't looking that good.
Right.
But every time I find anything, I correct it immediately, and the agent has it again. Every time the agent can't find something by looking it up through its reasoning paths, I have it explain it to me, and I then add those kind of search elements to the database. And so the next time around, Claude can find anything it's looking for. And so, or cursor or codex. And the past 2 or 3 projects, nothing's failed in terms of Claude searching. And so it's getting better. So I'm pleased so far. And now, you know, how many of us go to the documentation and say, remind me how to use let memory again?
Oh yeah.
How do I program this? How do I program this smart pin mode? Or how do I use the NCO modes? You know, it's just, and you ask Claude interactively, tell me how this works on the P2.
And that's the promise of AI.
It really works nicely.
Yeah. Be there with you and kind of guide you and hold your hand and help you get to where you're going.
Yes. And so now one of the questions I asked it when I started firing up this SD driver, I said, we've got this SD driver. It's a bit banging IO. It's very slow. It's got issues. Now you've got this P2 that I'm putting it on. What features of the P2 can I bring to bear to speed this thing up? You know, let memory, do I cycle sectors through let memory? Are there special data structures? How do I make sure I have good communication between all the cores and the back-end cog and things like this? And it came up with a whole treatise of which features, what performance gains I'd get, and what modes I can use for the smart pins. I mean, it really came up with some good research, reliable with respect to what we know about the P2 from the silicon documentation and the data sheet and the SPEN2 language reference. So a lot of fun seeing that happen. I don't know how we advertise that this feature exists or how we let people know, but I'm open to ideas because it's awfully fun using it.
Well, I think I'll start doing that for us. I didn't know you're working on that.
Oh my gosh, yeah, it's stunning.
I need to know, is there like a sample demo code that goes with it that writes data?
What do you mean?
For the SD card driver so that we could get people's eyes on it who don't want to write an interface to use it.
Oh, okay. Yes.
Is there a demo?
Yes. I haven't released the driver yet. It's within a couple of days. It uses cursor navigation for just like John's driver did for the Flash file system, John's demo. And let's see what I want. It has, Ken, maybe you didn't hear, I have a card formatter as one of the utilities that comes with it. I have the card characterizer and identifier. So if you see a card, if you're using a card that's not in my card catalog, you could literally run the benchmark utilities against your card and see how it performs against things I've tested. Those of us that are writing to microSD cards with the P2, we can cause our own brownout events by accidentally downloading code or by accidentally unplugging them. And that can damage potentially the file system. And so I have a full file system checker and it will do a repair. And so that's fully delivered with the driver as well. So let's see, what else do you have? The utility gives you the ability to format a card, to inspect the card, to find out what brand it is, and to change the volume label, things like that. And so look for my announcement the next 2 or 3 days, and I'll get this thing released. Did that answer your questions? Oh, tutorial, yes.
Sort of. I was thinking like about some way I could see it in use where I could just write some values to files or append a file and then
I created a whole page that is example file open, file read, file write, example directory behaviors, and you just study that page and it shows you all the code snippets. that comes with it.
People like me could even use that.
I'm hoping.
Okay.
I'm hoping that I'm providing the right level of documentation. If any of us that sees this driver when I've announced it doesn't find what they need in terms of things that will give them a leg up, please talk to me. I will generate a second perspective on this documentation very quickly if you need it.
Right.
I want this to be usable. I want it to be certified. I want it to be performant. And so that's where I'm going with it.
Well, yeah, okay. I'll give it a try, and I see Johnny Mack will as well.
Oh, very cool. Very cool. Thank you, John, for volunteering.
Yeah, we get Johnny Mack on board, then that brings John Huffman on board, and then we have some consumers using it.
Yeah, exactly. And then the thing I like is that having the flash file system, all of us were challenged with, well, how do we get files out there? And how do I get them over the P2 for the files that I want out there? And now having a unified driver for the MicroSD and the flash file system, you can do this now.
Yeah.
Robert Ash is asking a question. Be careful what you use. Robert, I need to know more context to be able to answer your question. He's asking, does Claude have personal usage memory? I love John's comment. What do you mean, Robert?
Maybe he means like, does it have continuity from like one session to the next? And like ChatGPT knows all the things I'm up to, so it ties those in other conversations.
That's because it's actually keeping a large amount of memory files around and pre-populating the system context with summaries of that. And Claude, all of them have that to some degree, but they have trouble through conversational compacting, as I said, or if your UI crashes, your command line tool crashes, there's a lot of trouble there, because if they hadn't written what they were thinking about to a file, it's not available again. And so what I found is that giving these things a way to remember what they're working on at the time they have discoveries, and then when you restart, all of that, no matter how many things they're trying to remember, is available immediately. They can go back and search through it and say, oh yeah, I was working on this. That has really helped. So no, I haven't found a CLI version, Codex, Cursor, or Claude Code that has a deep enough memory to remember what I'm working on. But what I do with any project I'm working on is we develop a detailed description of what the project is. And then we study the file system of the project if it already has code in it, and it creates a detailed description of that. And so between the goals of the project in detail and which files are in the system and what they're for, it's a minute or two spin up and you're back in context with your CLI working on the project. And then with a live external storage, I call this to do MCP. You can search for it. With a live external storage, it now has interim memory in between the documents it creates. And so I switch into a project, I start up Claude, and we are live full fidelity within 60 seconds of whatever I was working on last. And that is not a built-in feature.
Wow.
Yeah. It's all process. A lot of it is process. Develop a rich, detailed plan of what you're trying to do. Process. Tools don't do that by nature. Remember what you're working on and mark things complete as you complete them. Process, right? Develop a rich checklist for what you're going to be doing, and then mark them as complete as you do it. That's all process. And so that's how I get my forward development rate much faster than you can do with the tools by themselves.
Hey guys, thanks. I'm going to go. It was a pleasure, and I always learn something. Y'all have a good day.
Thank you.
Okay, thanks, Martin. We'll see you.
Thank you, Martin.
Bye-bye.
Ken, are you talking to us?
I was talking to you. You could read my lips.
Yeah, I wasn't doing that well.
No. Since we've had all the main topics, you could stop the recording.